Okay. This lecture for today is methylation reactions of biological systems. It is mostly a lot of methylation, but really this lecture is about single carbons at different oxidation states being added to molecules on that basis. One of them being carbon CH3 methyl group, okay, would be that. We had seen in the first semester, we had actually seen a single carbon molecule which was being combined with another molecule. And can you tell me either the type of enzyme or what was being combined with a single carbon at a relatively high oxidation state? Carboxylases, yeah, that's the enzyme, right? Carboxylases and CO2, okay? So we're going to be, we've seen that, okay, and we'll talk about it at this point, okay? The other thing about this lecture is that actually the three of the water-soluble vitamins that we didn't cover, okay, but that are in the vitamin lecture, they were pantothenic acid, which we covered a little bit in with the shift spaces, okay, so with that in the urea cycle in that lecture. And then we're going to do folate, okay, and we're going to do vitamin B12, okay, which is cobalamin, okay, all right? So that's what our process is going to be. That's the one, there we go, okay. These are the learning objectives. They can help you. I think you have them I tried to put them in front, okay, in terms of what's happening, okay? Good. All right. So here we have a full. Okay. I got to get a less lofty note page. Oh, I know what I wanted to have a question. Did anybody try that problem number 1 on the urea cycle? Yeah. Do you have any questions about it? Okay. All right. One of the ones was orotate, which is one of my favorite acids, orotic acid, okay, OROTIC, okay. We're actually going to learn about on Monday, okay, and it actually is made from CPS2, okay, and so that's what orotate was. When I was learning about the urea cycle, where is CPS1 function? What organelle is it in? Mitochondrion. Okay, and there was a belief that it wouldn't, because it has a high energy phosphate in it, that it wouldn't be able to get out of the mitochondrion. So that problem didn't make any sense when I was using the textbooks. Okay, so. But now we know that the carbamyl phosphate, which is made by 1, actually could go out. So by CPS1. So okay. You noticed if you have the 5th edition, well, the one online is the 5th edition. So you can. That's a useful one. If you understand that, you pretty much understand the deficiency diseases of the urea cycle. Okay. So here we have. Here we have the vitamin B6 is pyridoxine, that's the vitamin, and it has 2 different forms of this. This is pyridoxal, if this were a carbonyl, this is pyridoxal phosphate, okay? And it's forming a bond, double bond there, which is called a C double bond N, a shift space. In this case, it would be an aldamine, okay? Because it's between an aldehyde and an amino group. If it were a keto group that you were forming a shift space, it would be called a ketamine, okay? All right? Now, we actually did and looked at this. We actually looked at transamination reaction, okay? So what was happening is the pyridoxal phosphate in the enzyme is really functioning to anchor the amino acid, okay? So in transamination, okay? and work that way. But it also, the pyridoxal phosphate will function in a series of other amino acid enzymes that'll work on that, okay? And so one of the ones is actually decarboxylation. So what will happen in this situation is you have this anchored amino acid, and you're going to decarboxylate here because it's resonant, so you will lose that. So it's an amino acid decarboxylase. Okay, we're going to see one in the next 1 or 2 slides, okay? The other things that are important, okay, which we're going to see today, are beta elimination, okay, meaning at this point we're going to cleave this off, so this piece is going to come off, and we'll see that very soon, okay? Another is, and not terribly different, but it also has PLP, or amino acid racemization, okay? So what do you think racemization does? What's a racemizer? Remember R and S? How are they? What is the difference between?
50% of both of them, right? Like it's a mixture of both.
Yeah, but effectively, it's a mixture. So it would be R, and you could have one as a racemizer R, and S is another racemizer. Okay, what's the relationship? They're non-superimposable, but they're mirror images of each other, right? So that's what's happening. So you could keep it. All the amino acids that we find in proteins in humans is effectively there are L amino acids, okay? But there are bacteria and all kinds of ugly viri and things like that use D in any way. So they can be racemized using pyridoxal, okay? So pyridoxal, so pretty much if it's an enzyme working on an amino acid, probably pyridoxal phosphate or pyridoxamine phosphate, which is the opposite when you convert the ketone to an amino group, okay? Are there any questions about that? So, yes?
I was doing a question and said that PLP is used to, I guess, activate, or it works with glycogen phosphorylase.
Yeah, you'll see the glycogen phosphorylase. It is a wonderful National Board piece of trivia. Nobody really knows why, okay, but you need pyridoxal phosphate for glycogen phosphorylase. And what does glycogen phosphorylase do? It cleaves, yeah. It cleaves glycogen, one glucose molecule off by using what? Inorganic phosphate, right? You're adding across the bond, okay? And so you're doing it that way, okay? So good. That's a good question. I should have mentioned it, okay? So it's one of those pieces of trivia that it's used in that way. And I think when you look back in the vitamin lecture, it actually says that it's important for glycogen phosphorylase, okay? All right. So these are some reactions that actually use PLP, okay? I think we may have talked about this. This is glutamic acid. And what I'm going to do whenever we talk about amino acids, I'm going to tell you how many carbons it has in it and whether it's okay. In this case, is this acidic or basic or neutral? You know what? This compound. It's acidic, right? Because this and this actually neutralize each other effectively, and so it's an acid. Glutamic acid is C5. And this is glutamic acid decarboxylase, so it would work in that way as a decarboxylase. And we get gamma aminobutyric acid, which is GABA, and that is an inhibitory neurotransmitter, okay? And so that's a really important one because glutamate in the CNS is what kind of It's an excitatory, okay, and so one is converted to the other, okay? This one is really important, and we're going to see this reaction again. This one's is serine, which is a C3, has a hydroxyl group in this position, okay? So it's going to be polar because of the hydroxyl group, and it's a neutral amino acid, okay? All right, serine hydroxymethyltransferase. This group is a hydroxymethyl group, okay? All right? Is it more oxidized than a methyl group or less oxidized than a methyl group? More oxidized than the methyl group. And is it more oxidized or less oxidized than a carbonyl group? Less, right? Yeah. So it's in between. So it's methyl, then hydroxymethyl, and then the carbonyl, and we're going to see that later on. Okay? It's a very important one, and it's going to use FH4. FH4, we're going to see in a couple of slides, is folic acid, which has been reduced twice by NADPH. Okay? So it's called FH4, or in olden books, okay, like written by scribes and things on papyrus, okay, it's called THF, tetrahydrofolate, okay. So we're going to see that. It uses PLP, and now it gives us this product N5N10, methylene tetrahydrofolate, and glycine. So one of the things that you need to understand is that the breakdown pathway, this is the breakdown pathway for serine, the catabolic pathway, but it also is the synthetic pathway for glycine. So, right, do you see it? You're making glycine from serine, and serine is being broken down. So it's catabolic for serine, it's anabolic for glycine. Okay, it's one of the ways you can make glycine. Okay, and this uses PLP. Okay, all right. Single carbon transfer. Okay, okay. So here what we have is in this situation. Here's biotin, okay? So biotin is the most oxidized single carbon that biotin works on CO2, C double bond O, right? So it has two carbon-oxygen double bonds, single carbon. Biotin handles that. So that's the most oxidized one. Then we have, before that, formate. All right, before that is formal. Okay, we're going down. Hydroxymethyl, which is this CH2OH. All right, and then methyl, okay? Now, I'm going to tell you what's the other side of this. This is SAM, S-adenosyl methionine. 99.9% of methylation reactions use this S-adenosyl methionine. We're going to talk about this in the later part of this lecture, okay? All right? So most of them are that way. So the methyl groups all come from that. So when you hear about methylation of nucleotides or any of these things, it's always going to come from S-adenosyl methionine, okay? All right? So we have, this is the most reduced form, and this is the most oxidized form. Tetrahydrofolate, okay, is a cofactor which will allow the removal of this and using this producing when we're synthetic. So covers these oxidation states, hydroxymethyl, formal, and formate, okay? So here we have a cofactor which is working with carbons at different oxidation states, okay? And primarily, there aren't a lot of reactions that are used. So for instance, there's only one reaction that uses hydroxymethyl tetrahydrofolate, okay? It's just one, and it even has a different name, but we'll come back to that, okay? Is that clear to everybody? So we've got three different cofactors. Biotin, which we talked about in carboxylases, okay, which is what you were correct to mention, okay, at that point, okay, biotin. Then we have tetrahydrofolate covering these three oxidation states, and then SAM, okay? All right? And this dotted line says that SAM also does one reaction, which is used as the methyl form of folate, okay? That's really important, okay? And we're going to see what's happening. Are there any questions? Okay, this is a lot of chemistry, but it will be helpful, I hope, when you see it, okay? This is a schematic, all right, and but the only thing I wanted to show is that formal tetrahydrofolate, methylene tetrahydrofolate, and methyl tetrahydrofolate. This is methyl. Methylene, we're going to see, is hydroxymethyl, okay, and this one is formal, which would be the carbonyl form. Okay, everybody see that? Okay. And now, the products that we're going to get from it, okay, all the purines, okay, the purines are going to be synthesized de novo. Do you know what de novo means? From scratch, okay, from new things, okay? Things that were never part of a purine, okay, on that. So that's going to be important for the structure of that. Serine, actually, that reaction is reversible, and so you can go from glycine to serine using methylene tetrahydrofolate, and then B12 methyl group, okay? The active ingredient for B12 is cobalamin. Methylcobalamin is the cofactor, and that's used in one reaction, okay? And it comes from the N5-methyl that we're going to form of folate, okay? All right, so that's really it. I think it'll make a little more sense if we do and look at this way. All right, okay. So folate, the way to remember it if you want to do it is, if you wanted to eat a lot of it, it comes from foliage. Okay, folate, okay, leafy greens and all those things, okay, which is a good way to remember what it is. It exists in this structure. It has a pyridine ring, don't worry about it, okay? And it has paraminobenzoic acid, which is this piece, and then the glutamic acid, okay? The active form, so that's the vitamin folate, okay? And then it gets reduced by dihydrofolate reductase, okay? It isn't a dihydrofolate yet, okay? But this enzyme will handle both of these steps, and it will convert it from folate to dihydrofolate, okay? And then the same enzyme will then convert it to the active form, which is tetrahydrofolate, okay? All right, is that comfortable for everybody else? So that's the cofactor, and the active cofactor is the FH4. All right, just to tell you, this is tetrahydrofolate TH4. The active site here is not. Let's look, we don't need to deal with this. If you want to, you can deal with it. They'll refer to the positions for they'll be say 5 and 10, which is where it is actually going to be strung out. But let's take a look. The easiest one to do it is, this is N5-methyl tetrahydrofolate. So the methyl group is on the N5, okay, in the molecule. So if you went up here, you could see it with the number. It's this one, which is looking at that piece, okay? All right? Then we have methylene, okay? And then we have methanol, and we have formal. This formal form is equivalent to this form, N5N10 methanol. Some enzymes that use the formal level want to use methanol, and some want to use the formal form. But I can show you that they're equal because this is what kind of a bond? C and double bond N, a shift space. So if we add water to it, the oxygen is going to go to this position, right, as a carbonyl, and the two hydrogens are going to go here. And what we're going to get is that this one will turn out to be exactly the same as that, okay, just with hydration, okay? So those are equivalent, okay? This one, which is methylene, is CH2, okay, in the middle, all right? Whenever you see methylene, you'll see it where it gets a donor. It always means that methylene means that you're going to take it out as because you have this the carbon-nitrogen bond, okay? It's actually going to be hydroxymethyl. So N5N10 methylene is always going to carry from this form, it's always going to carry hydroxymethyl, okay? All right. Now, interestingly enough, this N5N10 methylene is only used in one reaction. Is only used when it's formatted. It actually picks up a hydroxymethyl group from serine and glycine, which we're going to talk about in a minute. Everybody clear with that? Okay, comfortable? So the oxidation state makes a difference. Okay. This is a relatively complex diagram, but it will help you to understand pretty much what's going on, okay? So if you want to break it down is, where are the sources of one carbon group? So where are they going? How do I get, we now know that serine is broken down by taking the hydroxymethyl group and broken down to glycine and then N5N10 methylene tetrahydrofolate, okay? So the hydroxymethyl group. So that's the source, okay? So that's it. And then the donation of the oxidized carbons, okay? And this is what they're going to be used for, okay? So what the folate derivative is going to be used for, all right? And then so we have 4 important reactions okay, which produce some of the folate groups associated with it at different oxidation states, okay? So if we start out, but the most important one, the primary donors to making N5N10 methylene tetrahydrofolate, okay, is serine and glycine, okay? And they get N5N10 methylene tetrahydrofolate, okay? Histidine, we'll come to this in a little bit, okay? Histidine, and we'll do that one at the same time, okay? Now, what we need to take a look at is that if I, for instance, make a lot of this N10 formal form, but I need some more of this form, which is the hydroxymethyl form, okay, I can actually convert it to that way, okay? And if I wanted to make more N5N10 methylene, which is the same thing, but if I wanted to make N5-methyl, okay, I could make it in this direction. What's important is, and what you're going to see, because it's going to show you problems when we start to look at disease states, is that once this goes from N5N10 methylene tetrahydrofolate to N5-methyl, it's irreversible, and you're stuck with the N5-methyl, okay, on that basis, okay? And that's going to be a problem when we have deficiency diseases, okay, all right, of the vitamins, all right? Other questions about that? Okay. Here's one of my favorite reactions, and we're going to go through this. This is the dump to dethump reaction, okay? Deoxyuridylic monophosphate goes to deoxythymidyllic, but you don't call it deoxythymidyllic acid because it's always made with deoxyribose, okay, so it's always set up that way. This is the reduction, okay, this is donation of the methyl group, and we'll see all of this, okay? Now, reaction 8, and we'll see this, okay? Methionine is essential or non-essential? Tim, the M and Tim, right? Methionine is essential, right? Okay. The problem is we can regenerate it. We can't synthesize it. What makes it, if you look at homocysteine, is a cysteine which is one longer, has one methylene more than cysteine, okay? And we can add the methyl group from N5-methyl tetrahydrofolate to homocysteine and make methionine. We're not synthesizing methionine, we're regenerating it, okay, with getting another source of methyl groups. That's the only reaction that N5-methyl does in the body. Very important for regenerating methionine, okay? All right, is that clear? And we'll see, we'll go through the lectures. We'll go through the steps in a little bit. Okay, all right. So here's reactions 1 and 2. So that refers to the number 1 and 2 on the back, okay? So here we have a repeat of serine hydroxymethyltransferase. Hydroxymethyl group is then going to be transferred. PLP is here, tetrahydrofolate. I'm going to get N5N10 methylene tetrahydrofolate and glycine, a 2-carbon amino acid, okay? All right. What happens to the glycine can go to glyoxylate and oxalate and all of those. This is not for this part when we talk about synthesis or breakdown of amino acids, okay? We're going to go and look at the oxalate pathway on this. So we're actually looking at just this. And then we have threonine, okay? And threonine has this hydroxy group. And what will happen is a hydroxymethyl group will be, PLP is involved, and this group is taken off, which is this group, and I get glycine again, and I end up, this glycine will then give me, also by glycine cleavage enzyme, okay, the same N5N10 methylene tetrahydrofolate and CO2, okay? So those are the major ways: breakdown of threonine, breakdown of serine, breakdown of glycine are going to be the major way I put carbon into the so-called folate pool, right? You can think of it as having, the folate pool is going to have carbonyl tetrahydrofolate, hydroxymethyl tetrahydrofolate, and methyl tetrahydrofolate, okay? And that pool can shift, except it can't shift from N5-methyl back to the other two, but the others two can actually shift to it, okay? All right, let's look at the next. All right. This is the histidine breakdown. Histidase breaks it to your kinase. Don't worry about it. What's happening in this situation, I have forming N-formamino-glutamate, okay, which is called fig glue. Why this becomes important is that the next step is it's going to combine with FH4 and give me N5-formamino tetrahydrofolate, which is another form of, at the oxidation level of an imine, okay, which is like a carbonyl, okay, but it uses tetrahydrofolate, okay. So we're going to find out if you have a deficiency in folate in the body, you don't make tetrahydrofolate. If you don't make tetrahydrofolate, you can't convert fig glue to glutamate, in essence, by adding FH4. So this is a chemical assay for if you measure the amount of fig glue, you can tell whether somebody has a deficiency of folate. It's going to become important because both a deficiency of folic acid, of folate, okay, and a deficiency of vitamin B12 in its activated form, which is methyl, are going to create the same problem. And if you've looked in that, I think somebody sent me a question: do we have to know all the deficiencies? It's just the ones that are broadcast are going to cause what? Does anybody remember what had to do with folate and what was the what? What? Say it again. Methylmalin. What? Megaloblastic anemia. Do you know what megaloblastic means? They're very, very large. And what are blasts? They're the precursors, okay? So they're going to be large cells, okay? So big problem, okay, in terms of that, okay? That's why you need to make a distinction, okay? So that's why this one is in here. And then this one is of interest because tryptophan will give you formate. Tryptophan is a essential or non-essential amino acid? What? It's an essential amino acid, okay? But interestingly enough, it also can be converted into nicotinamide, okay? So, and nicotinamide is, we get that also from niacin, okay? So if we have enough tryptophan in our diet, or in the protein in our diet, we don't necessarily need to take niacin, okay? In that. And where you see pellagra showing up is in things like corn, people who are on high corn diets, okay, there's not a lot of tryptophan in corn, and if they don't have another source of niacin, then they'll end up with, what was the niacin deficiency? Pellagra, yeah, thank you. Okay, good. All right, so that's just for completeness' sake, okay. So here we have my favorite, okay? All right, so deoxyribose phosphate dump, okay? All right, and we have deoxyribose D-thump, if you want to think of it that way, okay? All right, so I told you that 99.9% of the methylations are carried out by S-adenosylmethionine, okay? So you would expect that how are these related with one another? What's the difference between them? What's the difference between these two structures? What's the difference between these two structures? A methyl group. So what you would assume if you wanted to carry this out, okay, was that you would use S-adenosylmethionine, okay, as the methyl source, but that's not what happens, okay? All right. What we're going to do is use N5N10 methylene tetrahydrofolate. What's the carbon look like on that? Hydroxymethyl, right? Okay. So if I were to draw the intermediate, what we would have is CH2OH instead of that is the intermediate, okay? Hydroxymethyl group, okay? But that's not what we want to make thymine, right? Okay? So what we're going to do is use two of the hydrogens that we have from this then gets converted to dihydrofolate, okay? All right? And this gets reduced, the intermediate, which is hydroxyl, gets reduced to a methyl group, okay? So the cofactor, N5N10 methylene tetrahydrofolate, provides both the carbon, but at the wrong oxidation state, and it also provides 2 of the hydrogens, okay? So effectively, in order for this to be a complete cycle, we have to then convert this with dihydrofolate reductase back to tetrahydrofolate, okay? All the other times when the tetrahydrofolates, the formyl, the methanol, the methyl, whenever they donate, okay, they always go back to FH4. But this one, because you've got to reduce what you want, okay, and so it's important. If you want to only remember one enzyme, this one's important because also PLP is involved as well, okay, all right? So now there are a couple of things that are up here, okay? This methyl group is in the 5 position. I don't want you to have to know the numbers, okay, but that's the methyl group is in the 5 position. If I use 5-fluorouracil, okay, which has a fluorine in that position, okay, what will happen to this reaction? Well, if I give that, and it'll prevent, that fluorine will prevent the methylation that's occurring from N5N10 methylene tetrahydrofolate, okay? So it will prevent the production of DTMP. What's going to be affected? RNA, DNA? DNA, right? So you have something that's selective for DNA, okay, in terms of that, okay, and it works. It's used very reasonably in combination with another drug, which I'll talk about in a minute. It's used in combination with that for treating cancers, okay, and so it's 5-fluorouracil, okay? So that's why this reaction is important. The other one is methotrexate is an analog of dihydrofolate, okay? Or tetrahydrofolate, doesn't matter. It's an analog of this, and it inhibits this enzyme. So the combination of 5-fluorouracil and methotrexate, okay, actually prevents this from going back, because if you can't take the TH2 back to FH4, the FH2 to back to FH4, I can't keep this thing cycling, okay? Does that make sense to you? Okay? So it works in both sides, all right? So dump-to-de-thump is really an important enzyme. Yes?
You said that PLPs involve a
Yeah, it's not really. I realized that I misspoke. I'm sorry.
Oh, so it inhibits it?
What? It's involved in yeah. So it's not involved at all. No. Okay. So this is thymidylate synthase. Okay. All right. So it's the only one that uses hydroxymethyl. It's different than everything else. It's not like acetylmethionine. Okay. Okay. All right. So let's take a look at the next one. Okay. All right. This is B12. Okay. The important mineral that we have to remember, trace mineral, is that it contains cobalt. Rings like this that are like heme rings, okay, or similar to that, are called corrine rings, C-O-R-R-I-N, okay, and this is it. The active form, what you get in a bottle is the chloride here. The active form is methyl vitamin B12, okay, all right. Everybody see that? Okay. What's the important thing about vitamin B12 compared to all the other B vitamins? When you take a multivitamin, yeah?
It has to do with like the storage, I think.
What?
I think it has to do with, I guess, like you can store a lot of it as compared to other water.
Oh yeah, yeah. It takes about 2 years to use up your stored form in the liver. It's stored in the liver, okay? But suppose you were a vegetarian and you didn't eat any meat for 2 years. What?
You only get it from
Animal products. It has to be animal products, okay? So the reason I know the amount of times there was at Mount Sinai, there was a faculty professor and his graduate student who was actually Lewis Sullivan, who became the first first president of their medical school at I'm blanking, but one of the Georgia schools, okay? They starved themselves of meat products, okay, and showed that it was truly a vitamin because they went into vitamin deficient, they went into, guess what? Megaloblastic anemia, okay? So that was, they proved that it was that way, okay? All right? So it's an important one to deal with, meat sources. I had a medical student who was a runner in phenomenal shape. She went on a diet and a complete, no meat source or anything like that, and no supplementation of vitamins, okay? I remember she kept saying, I'm really feeling tired, so I asked her to do something. I went and said, spread your fingers like that. When you do that, do you see what my veins look like? They're red. When she did that, they were the same color as her palm, okay? And you couldn't see it. It's a good way to figure out anemia, okay, in terms of doing that, okay? You have to span the hand, okay? And then I don't know how. Right? Yeah. You're storing your blood inside, so not in your hands, okay? So, all right? So this is important. One of my professors in graduate school was on the group from Cambridge that did the X-ray structure of cobalamin, vitamin B12. What was very interesting, they did it in 1953 or 54, where there were no computers, okay? And this gentleman, and it's a lot of trigonometry and angles and stuff, he knew angles to seconds, all in his head. He never had to look in a book, and he would be able to put the angles to seconds, okay, and to be able to calculate this. It was brilliant. But it took without computers, it took them. I think it was the largest natural product that they were able to get the structure of. I think when they did the structure of that. So, okay. Now, vitamin B12 has a complicated history getting it into your body. Okay, and one of the issues is that there can be, especially in people in my age group, okay, some of the things break down in terms of getting it into the body, okay? All right. So what we're going to do is say this is the absorption, transport, and storage of vitamin B12. Okay, so here's dietary B12. That's in the CN form. By the way, the amount of CN in the body is very, very, very small, okay? So that you're going to take in, okay? So it's fine. So it comes into the stomach, so we're going to see the triangle. There are R binders, okay? And the R binders have a special name. They're called haptocortins, okay? And in the stomach, they bind the vitamin B12. The stomach also, from the parietal cells, releases intrinsic factor, okay? Intrinsic factor is another protein which is released from the the stomach lining, okay? Which then now we're going into the ileum, okay? The duodenum, and then what happens is the vitamin B12 comes off of the haptocortin, and effectively intrinsic factor binds into it and then protects it in this position, okay? So now I'm going to tell you a story about my father, okay? My father had from 1941 to 1954, my father had very severe bleeding ulcers, okay? At one point he lost 3 pints of blood on 2 days before Christmas, okay? At which point they decided that he was either going to die or they're going to have to do something. So he went to, we lived upstate, and my father went to NYU, where there was a guy who was treating bleeding ulcers like this by removing the stomach, okay? But he was really smart, okay? Because people who were actually, were other surgeons that were operating, they would take the entire stomach out. And in about 2 years, these people would then die, okay? All right. What they were dying was megaloblastic anemia, okay? Because they weren't being able to get enough of the vitamin B into the body, okay? This guy had a way of treating it. He left 15% of my father's stomach, okay? Which when my father, he left it and then closed it off. And he also treated them with liver shots, because at that time, vitamin B12 hadn't been really identified. The major source was from liver, because we store it in liver, and animals store it in liver and deal with it all that way. So he actually treated them. And my father then lived till 1995, okay? And he, at times he was over 200 pounds, okay? And when he had the surgery, he was 140 pounds, okay? So it's really important. He saved my father's life by being aware of what was going on in terms of that, okay? So you have to be aware of the things, in terms of what's going on, okay? The proteases then are essentially allow breakdown of everything, but this kind of protects it. And then there's another transfer of the triangle to this other protein, not important, okay? And then about 50% of this is in the portal circulation, goes to the liver, and then 50% escapes the liver and effectively goes to the other tissues. So most of it's stored in liver, okay? Does everybody see that? Okay. So the real problem is not having intrinsic factor and now not having the R binders, okay? So that the enzymes in that, we're dealing with it, so people will have it. As you get older, you don't produce as much intrinsic factor, so you then have to do it. Now, the important thing is, there was this guy that starved himself, tried to develop a new way of treating yourself for B12, and that new way was to effectively use an ointment that he would put up with vitamin B12 and put it up his nose, and it could be absorbed directly through the mucosa. Because the problem was you always had to give liver shots, which were really, kind of like liver homogenates, and they weren't terribly pleasant on that basis, okay? Because if you have to bypass this whole system, right? And so you have to give it directly into the blood and deal with it that way. Okay. So, all right. Okay. So we agree that it's important. Okay. All right. So what we're going to take a look at now are the relationship between tetrahydrofolate, B12, and SAM, or S-adenosylmethionine. Okay. So here's S-adenosylmethionine. Precursor gets methylated by that, and when you end up with it, you get S-adenosyl homocysteine. That's SA. So SAM goes to SA. Okay, that's what happens, and then that gets right S-adenosyl homocysteine. All right, SAM goes to SA, and then what happens is the homocysteine is released, and adenosine. The A stands for adenosine. I'm sorry. So we end up with homocysteine here. Okay, so there's an enzyme called methionine synthase, and put a quotation mark around the synthase, okay? Because we don't make methionine because it's an essential amino acid. What makes it an essential amino acid is the fact that the homocysteine is not made in the body, okay? And so we're actually recirculating it by the one methylation reaction, which is tetrahydrofolate, okay? And this is a methylase, and so effectively, that puts the methyl group onto B12, and then the homocysteine it receives the methyl group, and it goes back to methionine. Okay? All right. So B12 is going to be important for certain things to regenerate methionine, because we're going to actually have to make SAM. Okay. So what is SAM used for? SAM is used for a lot of things, okay? For instance, norepinephrine is converted by S-adenosylmethionine to epinephrine. So we have we have a neurotransmitter going to a hormone, which is also a neurotransmitter with that SAM. SAM, guanidinoacetate, takes SAM and makes creatine. Okay, I think we talked about creatine or creatine phosphate in terms of as a storage form. The nucleotides, they become methylated at this time by SAM. Phosphatidylethanolamine goes to choline, effectively with SAM. Serotonin becomes by SAM to melatonin. And we're going to talk about all these things like melatonin and stuff in later lectures, okay? And when we're talking about amino acids as being precursors to other compounds, okay? Is that kind of making sense for people? Okay. So now we have to deal with a situation of what happens when, uh, when we have a deficiency of either folate or B12, okay? So have I made the point that B12 and folate are both important? B12 is that way, okay? So what will happen, okay, under these circumstances? So you could have somebody who was low on folate, okay? And then what would happen? Well, when folate gets low, what's going to happen? And I have folate in the formal form, and then I have folate with hydroxymethyl, and I have methyl group. All right, okay. But I need it in this. I need it in this form, right? So the body then says, if it assumes that, that I need more methyl formate, okay. And now it's stuck in there. It's what's called methyl trapping, okay. All the folate becomes trapped on N5-methyl, okay. The other issue is that if I'm deficient in B12, after 2 years of being on a vegetable diet with no meat animal products, okay, you effectively end up in a situation where you don't have any B12, and I can't regenerate methionine, okay, so I can't methylate and deal with it. Now, there are really two issues, okay, and one of the things that you need to know is you need to know if it's a folate deficiency or a B12 deficiency or a combination of B12 and folate deficiency, okay? And the reason for it is that there are two different things that can happen, okay? You can see that there are neurotransmitters and stuff involved with SAM. So if I can so if I don't have enough B12 to make SAM, okay, then I'm going to have a problem which is neurotoxic, okay? So we're going to have problems with the nervous system, okay? If I am folate deficient, okay, I'm going to have problems with the enzymes, the enzymes that use the various forms of tetrahydrofolate. So for instance, I will see if I have folate deficiency, I'm not going to have enough of the folate form, to in essence make purines, so I won't be able to make purines. So what happens if I can't make purines? If I can't make purines, I can't make RNA, and I can't make DNA, okay? So it becomes a real problem, okay? All right? However, if I just give folate without giving B12, okay, I got a real problem, okay, because I'm going to still get the neurologic effects, okay? So I just give folate and not give B12, I'm going to have a problem because I'm going to solve the folate problems, the purine synthesis, okay, and all of those, okay. There's a reasonably good. You have to hunt the margins for the various deficiencies, diseases, and stuff, and so it's clear from that basis, okay. So you have to distinguish it. How could we distinguish it whether it was a folate deficiency or a B12 deficiency? We look at the fig glue, okay? How much fig glue do I have, which tells me that the folate is low, and so I can do it. That's why that becomes an important thing, okay? All right, and then I think we have some more, okay. There are only two reactions that use B12, okay? And you saw this already, okay? Which is, I'm sorry, this is one of them, okay? This is the one we just saw. So homocysteine with methyl B12, and effectively I get B12 released and I get methionine. So that's so-called methionine synthase. It's really methionine remake again, okay, redo, okay, that's the process, okay, so, all right, and then the other one is this one, methylmalonyl-CoA going to succinyl-CoA. Anybody remember the pathway? Odd chain fatty acids, okay, and so remember it goes, but with it, we're also going to have amino acids now, Remember, I think I mentioned the vitamin M group, valine, there is no vitamin M, valine, isoleucine, threonine, and methionine, okay? They all go through the same pathway, okay? And so we're going to see that in the same way. And I need B12 for that pathway, okay? All right? So that becomes important. And I think that's, no, okay. This is a schematic, and effectively what it's saying that B12 is important, and folate is important, and if you don't get it, you end up getting megaloblastic anemia. If you can't remember it, we all know what a megalomaniac is, right? All right? All right, and dealing with it. Okay, the cells become large. We have a problem with, we change the ratio of RNA to DNA in cells. The cytoplasm seem to not change, but the amount of other processes are problems. So you get these large, very large blast cells, okay, which are indicative of either folate deficiency or B12 deficiency, okay? And then with fig glue you test for fig glue, you can actually distinguish it, okay? Are there any questions about this? Yes?
So methionine synthase uses both folate and vitamin B12, is that correct?
Yeah.
Okay.
Yeah, you can't, because that methyl group has to come from folate, right? Right? From tetrahydrofolate. But that methyl group then has to go on to homocysteine to make B12, okay? To make methionine, okay? So that we can actually make SAM, okay? All right? Is that making sense?
Yeah.
Okay. B12 is that, okay? Other questions? Okay. Complex, not too, hopefully too bad, okay, in terms of it. But if you look for the marginal things in the you know, there are some good. It's in the same chapter as I think it's let me tell you. In 5th edition, it's in chapter 38, so the margin, so you look at megaloblastic anemia and deal with it that way, okay? So it's a very treatable disease, so, and preventable, okay, on that basis, okay? All right, so it's time to take a break,
Yeah,
okay?
so just come back at 2 o'clock on the dot, because
Yeah.
we do have a quiz at the end.
And now I'm stopping at 2:35. I hope that was...